So we spent quite a few, we heard quite a few talks this week talking about short GRBs coming from neutron star binary mergers. And I find it kind of remarkable that it has become accepted that these are the progenitors of short GRBs, because I think only a few years ago we didn't really have clear observational data to support this picture. So what I want to do in this talk is discuss what observations we have and what they actually tell us about the progenitors, and also what they tell us about the electromagnetic counterparts of LIGO sources. Okay, so these are the objectives. So I think first and foremost, for me as an observer studying gamma ray bursts, the first objective is to just determine what the population of short gamma ray bursts are, what their properties are, and then test the association with the mergers of compact objects. It's a model that's been around and has been very popular, and it's very attractive, but we really want to see if it holds up. And then if we can establish this connection, then we can use the properties of short GRBs to infer something about compact object binaries. That's part of what Zvi was talking about yesterday. Our process nucleosynthesis and the EM counterparts of gravitational wave sources. Okay, just to remind you what we're talking about, this is what a short gamma ray burst looks like. This is what a long gamma ray burst looks like. Overall, they are very similar in their gamma ray properties. The short bursts are somewhat harder in their spectra, but mainly they separate out in terms of the duration distribution. And so this is from BATSI with a separation at about 2 seconds. So what I'm going to do in the talk today is just use this canonical separation. And as Zvi mentioned yesterday, there might be some contamination. But as I'll show you, I think the separation in properties of short GRBs and long GRBs is so significant that that contamination, in my opinion, is actually rather small. OK, and then if we really want to understand the properties of short GRBs and what kind of environments they're in, then it's not enough to just look at the gamma ray data. Obviously, we need to go and find their optical afterglows, X-ray afterglows, radio afterglows, study their host galaxies. And so this is a large observational effort that my group and others have been carrying out for the past decade. And I think it's been quite successful. So to set the stage, let me just review what we know about long GRBs and the fact that they're connected with the death of massive stars. And I would say that there is evidence coming from 3 separate scales. Okay, and I'll use this to contrast with observations of short GRBs for the rest of the talk. So on a galaxy scale, long GRBs occur exclusively in star-forming galaxies. And not just any star-forming galaxies, but generally star-forming galaxies with young stellar populations, high star formation rates, relatively low metallicities. So they occur in an environment that support the production of very massive stars. On a sub-galactic scale, so within their galaxies, people have found that the offset distribution of long GRBs tracks the distribution of star formation in an exponential disk. So spatially, not only are they in star-forming galaxies, but they track the distribution of how star formation is distributed within galaxies. And their locations are also coincide with unusually bright ultraviolet regions. So regions in the galaxies that have particularly high star formation rates. Okay, so that's on a subgalactic scale. And then on the individual progenitor scale, they're associated with type 1c core collapse supernovae. And that association is both for the nearby low luminosity GRBs, and now there's a growing population of higher redshift, kind of full-blown cosmological GRBs. So there are quite a few of those with spectroscopic follow-up. So that, I think, that is, of course, I think the strongest piece of evidence. And we also find that their local densities on a scale of about a parsec. So this is the scale that's probed by the afterglow by the blast wave as it expands and produces the afterglow. The local density is relatively high. It's higher than the typical interstellar medium, and that is suggestive of mass loss from the progenitor stars. Okay, so that's the range of evidence. Now, what are the expectations for the compact object merger model for these same 3 scales? So on a galactic scale, we expect a broad distribution of delay times, which would lead to diverse types of host galaxies. So if the delay times are long, or at least some of them are long, then we would expect to find some short GRBs in elliptical galaxies. If they're generally short, we would expect to find more of them in star-forming galaxies. But overall, we expect a mix. On a subgalactic scale, we expect that kicks would lead to large offsets. Okay, and also weak correlation. If we ask how are they spatially correlated with both ultraviolet and optical light within their galaxy, there should be a weak correlation because the systems would move from where they were born, which is where the star formation and optical light are, to some different location where they eventually merge and produce a short GRB. And then finally, on the individual scale of the progenitor, we of course do not expect supernova associations. If we see a supernova association, that's a problem. Those kicks, if they're large enough, could also lead to the mergers taking place in low density environments, and so we might expect generally lower densities than the typical ISM density. We expect R-process nucleosynthesis, as we heard about, and that could lead to a signature in optical or infrared. And of course, we expect gravitational waves. Okay, so what I'm going to do is go through these points step by step and see how the observations match these expectations and also what they teach us about the progenitors. So let's start with the easy one, the lack of supernova associations. So here's one example of observations of a short GRB. So you can see the fading afterglow at early time. And then there are limits on a time scale of 10 to 20 days when we would expect a supernova to be bright. And what's shown here is the light curve of a type 1c supernova, but not the type 1cs that are associated with long GRBs. This is a much dimmer one. And you can see that even that can be ruled out quite easily. Okay? So that's one example. If we now look at the distribution, what we find, so what I'm plotting here is as a function of redshift, the limits for supernova associations for short GRBs in comparison to the prototypical brightness of a long GRB supernova. So you can see the various long GRB supernovae up here, and they have quite a narrow distribution of brightnesses. And those limits, as you can see, are much, much lower than that. Okay? Now, there are a couple of interesting things in this plot. So first of all, we can rule out supernova associations for these short GRBs, and we can rule out that they come from massive stars. The interesting thing is that all of these systems, all of these events occur in star-forming galaxies. Okay, so even though those events are in star-forming galaxies, the progenitor is clearly not core collapse supernova. Or
yesterday, Steve was mentioning even for long GRBs, the associations are only handful.
Well, you can see them up here.
Yeah, but
it's not a.
He was probably mentioning that only 3 or 4 of them are conclusive. So I wanted to hear your comment. I see the graph and many more than 3.
So I think it depends. So I would say that at this point, below about redshift of 0.6 or so, we actually have spectroscopic observations showing that they really are supernovae. Okay, so I would say below about a redshift of 0.6, these are spectroscopically confirmed.
Yes,
I think
most of them are with low luminosity galaxies.
Low luminosity no, the low luminosity GRBs are down here. There are these 4 or 5 at very low redshift. These are normal GRBs with normal energies. We can go over them one by one. These are not low luminosity. The low luminosity ones are below redshift of 0.15 or 0.2. These are things like supernova 1990 BW that's associated with GRB 98045. At these higher redshifts, intermediate redshifts, these are clearly events with energies of isotropic energies of 10 to the 52 and beaming corrected energies of 10 to the 51. What's the difficulty with the higher redshift? The supernova becomes fainter and getting spectroscopic data becomes more challenging. So, but it's not impossible, and so this is why this sample has been growing a lot in the last 2 or 3 years, because Swift is actually finding quite a few of these, and we're doing concerted observations to get those signatures. Now, when you go beyond a redshift of 0.6, spectroscopy becomes extremely difficult. So these at higher redshifts are based on the light curve shape. Now, you can argue that there's a conspiracy, that at these redshifts where we get spectra, these are really supernovae, and then here when we don't have spectra, things that look exactly the same shape and color like a supernova are not, and we just don't have spectra to confirm that. To me, that seems dubious approach. So I would say that these are, there's no dispute that these are really supernovae. And again, you can see that the range of brightnesses is actually quite narrow. I mean, there's a range of about a factor of 3 or 4 in brightness.
I thought there was some bursts where they didn't see a supernova, for a long burst where they didn't see a supernova.
So there's GRB 060614, which has a formally a duration that's long, and it doesn't have a supernova association. Now one could argue, so it looks like one of these short GRBs with extended emission, but even the initial component I think was about 4 seconds. Okay, and then it has this bump that maybe lasts 100 seconds. Yeah, so, clearly it's not a massive star, or there was such significant fallback that it did not make a supernova. Although you can see how much below it is, so it would have to be quite extreme.
So that one, so in principle at higher redshifts, it's more difficult to detect the supernova. Why that one is fainter than the others? That one.
This one?
Yeah.
I mean, like I said, there is a range, right? So,
observationally, observationally, at that redshift, can you still see the?
Yeah. So these measurements are generally with the Hubble Space Telescope. So the photometry is not so complicated, but getting spectroscopy out here is essentially impossible. Okay, but here we can do spectroscopy. Okay, the other interesting thing, so like I mentioned, these are all in star-forming galaxies. Okay, the other interesting thing, and I think that returns to Tzvi's point yesterday, is that if we look at the durations of these events, so these are swift events, the line that Tzvi mentioned yesterday was 0.7 seconds to separate collapsars and non-collapsars. 3 of the 4 have longer durations than that, but they're clearly not collapsars because they don't have supernova associations. Okay, so I would just use that as a word of caution of exactly where we draw that line. I think is still fuzzy, but I think to me the clear signature of something that's not a collapsar is the lack of a supernova. Okay, and then where we exactly draw the line of what separates long and short GRBs, I think is somewhat fuzzy. Okay, it doesn't mean that what Tzvi was saying is wrong. I think there is some uncertainty in where we put that line.
Just to confirm, these can't hide away, right? Supernova can't hide, unlike in our galaxy. Where
no, so because that's right. So that's a good point. So we can measure the amount of extinction from the brightness of the afterglow. I mean, from the afterglow itself, and just assume that the supernova experiences the same extinction as the afterglow, right? So we can correct for that. Yeah. Okay. So I think we can confirm, at least where we have measurements, that generally there are no supernova association. Now, this is not the full sample. We don't always have these measurements, but as a whole, whenever we have data, we don't see any supernova signature. Okay, let's look at the next stage, which is host galaxies. So one thing we find in the sample that clearly distinguishes it from long GRBs is that at least some short GRBs happen in elliptical galaxies. So I'm showing 3 examples here. This is an X-ray position coinciding with this galaxy at redshift 0.23. Here is an optical and radio afterglow detection, again coinciding with an elliptical galaxy at redshift 0.26. And here's another short GRB where the host galaxy is again an elliptical galaxy with no evidence for star formation at redshift 0.92. Okay, so at least some short GRBs happen in elliptical galaxies, and that matches our expectation that their progenitors can be relatively old. Now, there's an interesting test that we can carry out that tells us something about the age distribution, which is the following. If the progenitors are generally older than a gigayear, which means that the rate only tracks stellar mass, so the more stars I have, the more progenitors I'll have, then we would expect that half of short GRBs would be in star-forming galaxies and half of them would be in elliptical galaxies, because that's the distribution of stellar mass in the universe. Okay, so out to about redshift of 1, where this sample is probing, roughly half of the stellar mass is in ellipticals and half of it is in star-forming galaxies. Now, if the progenitors are younger, or at least some of them are younger, then we would find an overabundance associated with star-forming galaxies because they would be influenced by star formation in addition to stellar mass. Okay, so we can go and actually count. So here is the full sample, everything that we have, and we find that about half of them are in star-forming galaxies, only 15 to 20% are in early type galaxies, ellipticals. 20% are inconclusive, so they're relatively faint. And about 15 or 20% are hostless events, which I'll come back to. They don't have a galaxy directly at the position of the afterglow. Now we can place other cuts. For example, in this last panel, I'm showing a cut that's based on the analysis that Zvi was talking about yesterday. So we took their probabilities of what is likely to be a collapsar and what is likely to not be a collapsar. So this sample is somewhat smaller. It's 14 events. And you can see that things don't change. Even in this sample, which would be in that analysis considered more or less purely non-collapsar events, most of them are in star-forming galaxies. Okay? So what this is telling us is that both stellar mass and star formation influence the short GRB rate. And that ratio is roughly consistent with a distribution that goes like tau to the -1, a merger distribution. Okay. Yeah?
So for long GRBs, if you do the same exercise, do you also have those inconclusive ones?
Yes, especially at higher redshifts where getting spectroscopy is difficult, and sometimes we don't even see the host.
And the fraction is also more or less 20%?
Yeah, I mean, the issue with something like this is you can look at the colors of this galaxy, and it doesn't look like an elliptical galaxy, but it's too faint to take a spectrum and directly confirm. And so I would say that most of these inconclusives are likely belong in this category, but we try to be conservative about how we define something as being a star-forming
How
galaxy.
about hostless? For long GRB, do you have hostless ones?
That analysis has not been done carefully. Yeah.
Sorry, what did you do between A and B? You said, but I think I missed.
So what we've done going from here to here is something that I'll come back to in a few minutes, is for these events that lack galaxies exactly at that position, we asked is there a galaxy in the field that has a low probability of chance coincidence, and we argued that that is the correct host and then assigned them to these categories. Okay, but I'll come back to that argument later.
If there was a minimum delay time
Mhm.
for the short GRB, how small would that delay time have to be to get enriched in star-forming galaxies?
I think that even a delay of a few 100 million years would still give you the same result. Big-
If the minimum delay time was a gigayear,
A gigayear wouldn't work because you wouldn't see this this effect. So I would say something like 200 or 300 million years. Okay. So so let me show you. So that's looking at the demographics, just counting how many are ellipticals, how many are star-forming galaxies. There's another way to look at this. So what we can do is we can take we can measure the stellar masses of the galaxies, infer them from doing model fitting of galaxies. It's a well-known technique. And we can ask, if I take those masses and ask the following question, let's say that I take the mass distribution of the ellipticals. Okay, so that's the red curve over here. And then I ask, let me take the mass function of elliptical galaxies and draw from that mass function normalized by mass and create a distribution of what the masses would be. Okay, so the mass function of galaxies is just number as a function of mass. And I'm asking what would actually be the mass distribution of if I drew galaxies from the mass function weighted by mass, which means that I just take a short GRB and I say, short GRBs are just proportional to stellar mass. Then I find this magenta curve, which agrees with the actual masses that are measured. Okay, so what this is telling me is that the masses of the ellipticals, not just how many elliptical galaxies I have, but what are their actual masses, agree with just drawing galaxies from the mass function weighted by mass. Now we can repeat the same exercise for the star-forming galaxies. So my expectation is this cyan curve, and the actual mass distribution is in this range over here, in this blue range. Now the reason there is a range is that this is the most likely number. And this maximal number, this curve that has higher masses, says, let's say that these galaxies are somehow hiding huge populations of very, very old stars that were formed at redshift 20. Okay, it's really unlikely, but it just gives you the most extreme value. But this is the likely curve. So what you find is that the masses here are systematically lower. Okay, so what this is telling us is that the rate per unit stellar mass in star-forming galaxies is about 3 times higher than in elliptical galaxies. So what does this mean? It means that something else is controlling the rate, not just the stellar mass, and that something else is the star formation rate. Okay, so I have more short GRBs or more progenitors of short GRBs per unit stellar mass in star-forming galaxies. And that's identical to what people find for type 1a supernovae. Okay? So again, this is pointing to the idea that the short GRB rate is proportional to both stellar mass and star formation activity. And that means that some of the merger timescales in the context of neutron star binaries are relatively short, again, in the range of a few 100 million years. Okay, they can't all be very old. Okay, finally, we can look at the actual ages of the stellar populations in these galaxies. Okay, and say if the progenitors were formed at the same time as the dominant population in the galaxy, what would be the age distribution? Okay, so again, essentially the ages of the stellar populations are like a chronometer for the delay time. Okay, and what we find is this distribution in black. So you can see that it ranges there from something like, 50 million years up to 3 or 4 gigayears. Okay, and there's quite a broad range, and the events in the star-forming galaxies have a typical delay of about 0.3 gigayears. Okay, so again, it's, the sample is relatively small. It's hard to fit an actual delay time with great significance, but I would say it's at least consistent with something like tau to the -1. But you can see that it's hard to explain this with as we mentioned yesterday, they were finding a delta function at 3 gigayears. That would be really hard to explain then why there are so many events happening in galaxies with these young stellar populations. Okay, so that's about the delay time distribution, and essentially looking at the distribution of host galaxy types and the properties of those host galaxies suggests that there is quite a broad distribution of delay times. All right, let's move on to the sub-galactic scale. Okay, so this idea of kicks.
But is this distribution consistent with the distribution from the galaxy galactic population?
The tau to the well, as we mentioned yesterday, the galactic population potentially looks like something like tau to the -1. There aren't that many sources, so at least it's consistent. So I think there's an overall consistency, but both populations are relatively small, right? So I think it's. But
short mergers, we don't see that many, right?
Well, so like I said, the range that we find is something like 100 million years to a few gigayears. The shortest merger timescale in the Milky Way for an observed system that hasn't merged is a couple hundred or of order 100 million years. So I don't think there's a discrepancy there. Yeah, it's me.
Since you're moving to another topic, I just want to mention that in the current observed population of short GRBs, if the time delay is so short, there should have been more low redshift short gamma rays. Now, there is absolutely no bias that I can imagine against the text detecting or measuring the redshift of a nearby burst.
No, I don't understand that statement at all. If the delay times are short, you would expect to find more at higher redshift because the peak of the star formation history is at redshift 2 or 3. So it would give you more at higher redshifts, where I think it is difficult to get the redshifts because we're getting them from the galaxies. So I don't think it would add, I think that this would push things to higher redshift rather than to low redshift. Because there's very little star formation in the present day universe.
But the overall trend that you're finding, that you have more smaller mass galaxies, is fine, because if you have more smaller mass galaxies, then in smaller mass galaxies, the star formation rate is delayed relative to the average star formation.
Okay, so what I should have, yeah.
So this delay, even with 3 gigayears time delay, will give you delay relative to the average population.
Okay, so
this result is completely consistent. These two results are completely consistent.
no, so let me disagree with you for the following reason, and I should have shown the. So what I said is that the masses of the star-forming galaxies are somewhat lower than one would expect, drawing from the mass function by mass. They are still much more massive galaxies than the host galaxies of long GRBs. So, and even for long GRBs, we see that most of the population is a much higher redshift because that's when the peak of the star formation history is. So I don't see how that would be the case. It's true that as you go to lower redshift, star formation is shifting to smaller and smaller galaxies, but much smaller than these. So these are kind of L-star galaxies like the Milky Way, where there's very little star formation activity at the present compared to what it was in the past.
Then you need a time delay. Then you need a long time delay.
No, so what I'm saying is that you would find that we are probably missing things at higher redshift. That would be my expectation, that the delays are generally more like a few 100 million years, not several gigayears, and we're missing things at redshifts 2 and 3. Because Swift isn't...
For instance, the Milky Way, they're all gone.
Well, I'm saying that the Milky Way has a much lower star formation rate at present than it did at redshift 2.
So it's gone. And all the
Well, it's still making binaries, but at a much lower rate. Yeah.
So that, would you then extend to say that the radio binaries that we find, the rate that is inferred might be a lower estimate or something?
So,
Because it's not making those binaries anymore at redshift 0.
I have to think about this a little bit. I mean, I think that the numbers that Zvi showed yesterday are probably quite reasonable. And again, I think, as he pointed out, the main issue is not so much the delay time, which can move things up and down by maybe a factor of 2, but what is the minimum luminosity, which can increase things by an order of magnitude. So, yeah.
Can you rule out lower merger time? Like, can there be a sizable fraction with 50 megayear merger times?
Probably not, given that I think that if there was a sizable population, we would essentially start finding these things in the same types of galaxies as long GRBs. And they are quite different in all of their properties. They have higher masses, they have lower star formation rates. I guess what I'm saying is star formation is influencing that rate, but now with a very short delay where you would still see them in the kind of starburst phase. Okay. All right, so let's move on to the this question of offsets or the locations of short GRBs within their galaxies. So to measure this, we need higher resolution images, so we need a Hubble Space Telescope. So I'm showing here just an example of 6 different systems where you can see the galaxy and you can see the position of the afterglow marked in a red circle. Okay, and so just visually you can see that some of these are quite far out from the centers of the galaxies, and some of them are close to the center. So the question is the distribution. That's what we want to look at. Now, before I kind of put all of this together, I want to come back to these events that I called hostless bursts previously. So what's the deal with these sources? So the idea here is that we have optical positions. We have very precise positions for the afterglows. And when we go with HST, both in the optical and infrared, and get very deep observations, we don't see any galaxies at the positions of the afterglows. We see galaxies around those positions, but not exactly at that position. And so one interpretation is that these are events that have very large offsets from their host galaxies, that they came from some other galaxy and just traveled a large distance. So by the time the event occurred, it is no longer spatially coincident with the galaxy. Okay, so how do we evaluate this possibility? Well, one thing we can do is we can take each galaxy in the field and ask what is the probability of finding that galaxy by sheer coincidence. Okay, so for each galaxy, we calculate the probability by taking the number density of galaxies of that brightness multiplied by the area that we're searching. Okay, and the probability is just given by 1 minus e to that product. So that means that, of course, galaxies that are faint are more numerous on the sky, whereas galaxies that are bright are less numerous, but maybe we're searching over a larger distance. And essentially what we're looking when we do this analysis is for some galaxies to have a very low probability of being there by chance, which would suggest statistically that those are the host galaxies. Okay, so we do this and we repeat this for all the systems where this occurs, and we looked at the cumulative probability.
You weighted by the probability that the object will be kicked from the galaxy, because if you have a more massive galaxy, the object has lower chance to be kicked out of it.
No, because I think the idea here was not to impose any specific model on this in terms of what kick velocities we expect or anything like that, but just to look at this in a very But I'll show you in a second how we normalize this, which I think will take care of any concern like that. Okay, so when we do this for all these fields of the hostless short GRBs, we take the cumulative probability and we find that at separations of a few to maybe 20 arc seconds, there's a very low probability of chance coincidence. Whereas at smaller and larger separations, there's nothing obvious. Okay? So this suggests that in those fields, there are galaxies, like for example, in this field, it's this particular galaxy that has a low probability of being there by chance and therefore might be the host. Now, again, I want to stress this is a statistical statement for the population. It doesn't mean that on a case-by-case basis, they're all correct associations. Now, we can repeat so one concern is that maybe this is a spurious result that has nothing to do with short GRBs. We can repeat the same exercise for events that have coincident galaxies and see if we find a similar signature. And the answer is no. So for the ones that have coincident galaxies, the low probability is at very small separation. That's the actual galaxy we call the host. And there's nothing else in the field that has the same signature. Okay, so there's something special about the fields of these hostless GRBs, which means that they are coming indeed, or at least as a population, they come from these galaxies at very large offsets.
Well, you know, actually, I have asked this in the past.
Yeah.
Is it possible that there are these low luminosity galaxies, right?
Yeah.
You know, is it possible that they are hiding in those?
Yeah, so you can kind of reverse the question and say, let's say that they came from galaxies that are similar in brightness, in luminosity to the other host galaxies. And I just push them to higher redshift so that I don't detect them in my images. So what redshift do I have to push them to drop below the detection level? And for it, generally, it's something like redshift of 3 or so. Okay, so I have to push them to quite high redshift for them to not be detected.
But there are also these so-called intrinsically low luminosity.
Sure, and so then you can play a third game. You can say, let's say that they're at similar redshifts to the other ones. How much do I have to decrease the luminosity to hide them? And then I have to decrease them to something like the Small Magellanic Cloud or lower. So if I look at the distribution of galaxy luminosities, it would create a large gap. There are a lot of kind of fairly luminous L-star type galaxies like the Milky Way, you know, fairly large ellipticals. And then I have a big gap, and then I have a bunch of them happening in things like Small Magellanic Cloud. So I think both the high redshift and the low luminosity ideas are problematic. But again, even if those were the case, then what's going on here? You know, why are we seeing this, these low probability galaxies in those fields?
What if you randomly throw dots in the sky and do the same exercise? Do you see this dip or no?
No, I mean, so that's essentially what's done here, right? I just took a different sample that has coincident galaxies. That's like throwing darts on.
But they're still related to short GRBs. If you have a host galaxy there, then
yeah, no. So does it? So
randomly throw dots in the sky.
yeah. So there's another paper that followed up on this from Neil Tanvir's group, where they've essentially done that. They took the same images, so they're using the same data, but so the number that goes in here comes from galaxy surveys, right? I mean, the important number is how many galaxies there are per magnitude on the sky. Okay, that comes from galaxy surveys, which essentially is like throwing darts at random. But what they've done is they did this empirically. They took the same images, and instead of just taking the position of the short GRB, they took a bunch of positions on the image. And they found essentially the same thing. Okay, so now what we can do is we can go to those fields and get spectra of these galaxies and see what kind of galaxies they are, what kind of redshifts. And we find that they're generally at redshifts of between about 0.1 to 0.5, 0.6. So similar redshifts to the rest of the short GRBs. And those separations correspond to something like tens, maybe up to 100 kiloparsecs. Okay. All right, so if we fold all of this together, we find the following. This is the red histogram here, is the cumulative offset distribution for short GRBs. And we have comparisons here to long GRBs, core collapse supernovae, type 1a supernovae. But I think the more interesting one is the comparison to population synthesis predictions for neutron star binary mergers, which are these gray lines. And you can see that overall there is reasonable agreement. In particular, there's reasonable agreement here at the large offset tail of the distribution. But again, I want you to notice that quite a few of them, at least 50%, occur within 10 kiloparsecs. That means that they're at least coincident with the spatial extent of these galaxies, and it's only about a quarter or so that have these large offsets.
What are the different larger models?
It's, you know, people like Chris and then Chris Bolchinski and, you know, other. Yeah, I mean, you know, they each have their own code and. Yeah.
Sorry, question. This is the projected offset.
Yes.
Is it, from the observational point of view, any chance to understand if this is a projection issue or not? Let's say maybe the physical distance from the galaxy is still high, but it's just pointing at you so that you don't. It seems to be online.
Yeah, I mean, I think that's possible. I don't see a reason why there would be a preference for this to happen very often. So I think you can just assume that it's
you can treat it statistically,
yeah.
Just with an average
Yeah.
angle, and
Yeah, exactly.
can be in the statistics.
Yeah. Okay, and then we can also look at it slightly differently. We can ask, instead of how many kiloparsecs away, we can ask what's the distance from the galaxy in units of the size of the galaxy, the effective radius of the galaxy. And what you see again is the following, that there's a tail to very large separations, you know, many times the effective radius. And for example, we find that 20% are at greater than 5 times the effective radius. And if you ask what fraction of stars reside at such large separations from their galaxies, it's only of order 1 or 2%. Okay, so there's an overabundance of short GRBs at large offsets compared to stellar populations in galaxies. All right, so that's one indication for kicks. We can look at it in another way by making this very complicated diagram. So what's shown in this diagram is the cumulative distribution of the relative locations of short GRBs, where by relative location I mean the brightness at the position of the short GRB relative to the rest of the galaxy. Okay, so just to kind of guide you, distributions that are on this side of the diagram are particularly strongly concentrated on the brightest regions. Okay, so for example, if you look at long GRBs, okay, and you compare them to the distribution of ultraviolet light in their host galaxies, you find that quite a few of them happen at the brightest 10 or 20% regions. Okay, you would expect that half of them would be in the brightest half. Right? You would expect things to kind of lie along this diagonal line, but long GRBs are particularly strongly concentrated on the brightest UV regions. Okay, now the gray line is core collapse supernovae. You can see that those are closer to the line. Generally, they just track where star formation is happening. Now, if you look at short GRBs, okay, so the corollary of that is that things in this part of the diagram are weakly correlated. Okay, so if we ask the question, what is the correlation between short GRBs and ultraviolet light, so star-forming regions, we find this blue curve. And you can see that that correlation is very weak. And that shouldn't surprise you because we already determined that short GRBs don't come from very young massive stars, so they shouldn't concentrate in bright star-forming regions. But I think what's more striking is the red curve, the thick red curve, shows the correlation between short GRBs and optical light. Again, optical light tracks just the general population of stars, old stars, not young stars. And even here we find that something like 40 to 50%, so close to half of all short GRBs, occur where there is no detectable emission at all from the galaxy. Okay, so things like here or like here where there's very little emission. So what is this telling us? How is it possible that we have a population of stellar objects where half of them occur where there is no stellar objects? Okay.
Those are associations, clear association, right? You're not saying they're not.
Yeah, so this doesn't even include the ones at very large offsets. These are systems like this where, you know, you're close to the galaxy, it's unlikely that this is a chance coincidence, okay? And that's roughly half. So the way to do this.
So and the 1As do what makes sense. You know, they're there where the stars are. They're in the optical.
Yeah, and they're fairly weak in the.
They're not there.
Yeah.
They're not in the star.
Yeah,
Okay.
exactly. And so this is again. This is a somewhat different way to look at the problem, but it leads to the same conclusion that the progenitors are traveling. They must have been born where the stellar mass is distributed. But by the time we see a short GRB, they're decorrelated from where the stellar mass is. So the only way to do it is to just move them around, okay? And that's what we expect for kicks. Okay, so I think we have reasonable evidence for these kicks. Okay. All right, so let's go to the individual progenitor scale. I already talked about the lack of supernova associations. Those kicks would also predict that we should find fairly low densities, at least in some cases. So how do we do that? Well, to infer those densities, we need to go to the afterglow. Yeah.
Quick kicks.
Yeah.
Can you say something about the magnitude of the?
Yeah. So the way we've looked at this is the following. We took the ages of the stellar populations that I showed previously for each one of these galaxies, and we took the offset, and we said, what if the age of the progenitor is the age of the stellar population, and I know how much it traveled, at least projected, then I can get a kind of a rough projected velocity, and then look at what the distribution of that is. And those numbers are in the range of, I think, something like 30 to 150 kilometers per second. So at least in part, what this is telling us is that the kicks don't have to be large enough to unbind the system from the galaxy. It just needs to put it on an orbit where it has fairly large separation from the galaxy.
With this velocity, with 30 kilometers per second, you cannot get out of a Milky Way galaxy.
So, but like I said, not all of them are. I mean, it's only a quarter that have these very large. So the smaller velocities are for things that are only within a few kiloparsecs. But the ones that are at large separations, 30, 50, 100 kiloparsecs, those are the ones that need more like 150.
But also with 30 kilometers per second, to move 100 kpc.
No, but that's what I'm
you need
saying.
More than a GWIEM.
Yeah, so that's what I'm saying. So those are the ones at larger separation require larger velocities. So more like 150, 100 kilometers per second.
It's a lower limit because it could have gone out and could be orbiting in some, right? I mean, it could be a double pass, right? I mean,
Yes, yeah.
it doesn't have to have been the first.
Sure, that's true.
I mean,
yeah.
so the population synthesis included all that when they made, when we took essentially the pulsar velocity kick distribution, put that in, made the binaries, they got kicks. And so when you compare it to them,
Yeah.
and we put them in orbit, so we actually did all that.
Yeah.
So observational, do you see the correlation? The larger offset ones indeed have an older population in the galaxy?
The larger offsets, not necessarily, no. But big, and I don't. But it, you're convolving two distributions. You have the velocity, the kick velocity, and the merger time scale. And so, and then given the size of the sample, it doesn't surprise me that we don't see a very strong correlation there. Okay, so let's look at the density. So the way we infer the densities is from the brightness of the and the properties of the afterglow. So I just wanted to kind of show you how we do this. So this is the basic synchrotron emission model for the afterglow. So it has several components, several segments. And the important part is that different segments give us a view of different parameters. Okay, and I'm dropping for the moment the microphysics, the fraction of energy that goes into electrons and into the amplifying the magnetic field. And I'm just looking at the kinetic energy, the isotropic kinetic energy of the blast wave, and the density. Those are the two primary parameters. And so these different segments give us a different way of measuring these combinations. And it works out that radio observations generally probe this part of the spectrum, optical this part, and X-rays somewhere either just above or just below this cooling break. Okay. Now, we don't have detailed observations for every short GRB. And not all of them are even detected. So you can see that in X-rays, actually, the detection rate is very high. It's about 90%. But in optical, it's already lower. It's about 60% or so. And in the radio, it's something like 10%. Okay, so that means that we won't be able to get very detailed measurements for each one, but we can try to see what we can get from the overall distribution. Now, in some cases, we have detailed observations. So here's an example. This is what I showed you previously was schematic. Here's what it actually looks like. So here's radio observations on this part of the spectrum, optical infrared on this part, and X-rays on this part of the spectrum. And so given the uncertainties in the measurements, we can infer some of these properties. So the kinetic energy is something like 2 times 10 to 51. The density is somewhere in the range of 0.01 to 0.1 particles per cubic centimeter. Okay, so that's already lower than typical interstellar medium densities. Here's another example where we have radio, optical, and X-ray observations. Here we actually see signature for jet, which I'll come back to in a few minutes. So we can actually get the beaming corrected energy. We find that it's about 10 to the 49 for the kinetic energy, and the gamma energy is also about 10 to the 49. And again, the density is low. It's something like 2 times 10 to minus 3 particles per cubic centimeter.
The same question asked Brian the other day. So did you fix epsilon E, epsilon B for these calculations? What if you throw in some epsilon B's?
So yes. So you have to do. You don't have enough information to fully constrain it. So what we've done here is take epsilon E of 0.1 and epsilon B of 0.01. And of course, as you change those numbers, these numbers will also move around. Okay, and here's another more recent example. This is GRB 130603b. That's the one with the possible kilonova. Again, we have radio, infrared, optical, and X-rays. And again, we get beaming corrected energies of about 10 to the 49, very similar to this event, and density of, again, somewhere in the range of 0.01 to 0.1. Okay, so these are, to some extent, our best studied cases. Now, what can we do with the other ones? Well, we can at least place some constraints. So if I make a parameter space, now here I'm using 0.1 for epsilon B and epsilon E. Okay? If I make a parameter space of energy versus density, if I have X-ray observations, they give me a measure of the kinetic energy. If they're above the cooling frequency. Optical observations will give me some degeneracy line of both energy and density. If I have a radio, in this case I have a radio upper limit, so it rules out some part of the parameter space and allows the rest of it. And finally, I can use the location of the cooling frequency itself to place another constraint, so everything on this side is ruled out. Okay, so even though I don't have very detailed measurements, I can look at the intersection of all these places, of all these constraints and what's ruled out, and I can essentially get a measurement or a range for the energy and density. So in this case, we find that the isotropic equivalent kinetic energy is somewhere between 1 and 0.9 and 1.4 times 10 to 52, and the density is somewhere in the range of 2 to 6 times 10 to minus 3. Okay? And now we repeat this exercise for 20 GRBs, and we can make distributions. Okay, so this is the distribution for densities, and this is the distribution for the isotropic equivalent kinetic energy. So you can see that the typical, or the median, is about 2 times 10 to 51 here, and here the median is of order 10 to the minus 2 particles per cubic centimeter. Okay, so that agrees with the cases where we had detailed measurements, which were all in the range of somewhere between 10 to the minus 3 and 0.1. And these are the typical numbers for long GRBs. The density is of order 1 particle per cubic centimeter or somewhat higher, and the isotopic equivalent energy is about 10 to the 53. Okay, so very different ranges. But you can see that systematically we find, although there's a range in the densities, generally they're reasonably low and below the typical interstellar medium densities. Now, I should mention, again, as Bing pointed out, this curve would shift to the left or to the right if I choose a different value of epsilon b. Okay, so if I reduce epsilon b by a lot, then this curve will shift up to higher densities. Okay.
It may change completely if UC becomes above mu x.
Yeah, so there.
When you reduce epsilon b, you can get to the situation that mu c is above epsilon.
That's right. So
above mu x, and then this change completely.
Yeah, but what we do is we actually infer the location of nu c from the data, from the relation between the decline rate and spectrum of the X-rays compared to the optical. Okay, so we can, in some cases, we see that nu c is indeed above the X-rays. In some cases, it is below. But all of this is already folded into this. Okay, the other interesting thing we can get from the afterglow is beaming, and of course that's critical for two reasons. One is it's a correction factor to the energy scale, and the other one is it's an inverse correction factor to the rate. Okay, so the way we measure opening angles is by looking for these breaks, the jet breaks, and we now have a few measurements and some lower limits, and you can see that there's quite a range. The measurements are somewhere in the range of 5 to 7 degrees. We have some lower limits that are greater than 10 degrees. Again, it's with the small numbers, it's hard to say this is the typical number, but if we take something like 10 degrees as a typical opening angle, then that means the typical energy scale is about 10 to the 49 ergs. And the correction to the rate, so I took the number from what Zvi showed yesterday, 5 per gigaparsec cube per year for the observed rate, and then using this correction factor, the rate within the LIGO detection volume is somewhere in the range of 5 to 50 per year. Okay? So that's good. That means that if this whole story holds together, then LIGO should detect quite a few events. And if we go several years without any detections, then at least some part of the story is broken.
What do you assume for the range? I see other people quoting 300 megaparsecs.
I use 200. Where, I mean, isn't 200 the
200
official
is,
number?
The so-called angle averaged distance, right? And I think that's the right one. 300 might be a bit too much.
Yeah.
But on the other hand, I saw Horizon being quoted 300, but Horizon is more like 450.
Yeah, no, so I use 200 for the
200,
range.
yeah.
Yeah. Okay, so yeah, so we seem to have evidence for these kicks from the low densities that we infer. Okay, let me, so I don't want to say much about this because Brian talked about this in great detail. He showed the impact of high opacities on the emission from the kilonova, shifting it into the infrared. And he also showed the observations of 130603b that show at late time excess infrared emission without accompanying optical emission, right? So, so we have plots like this that show this excess above the expectation of the afterglow by about a factor of 30 that roughly match the expectations of these kilonova models with inferred mass of about 0.03 or maybe 0.05 solar masses. Okay, so I think that's, at least in this context, this is right now our strongest piece of evidence, that one detection. And hopefully we'll have more of these in the future. All right, so in the context of gravitational waves, I'm not going to show you that we have a detection, and I'm not going to put a check mark there. That's for the future. But I do want to go back to this issue. Now that we have, so what have we essentially inferred so far? We inferred the energy scale, we inferred the beaming, and we also inferred the density of the surrounding medium. Now, the density of the surrounding medium will be the same whether we're viewing something on axis or off axis. So we can use that to predict the brightness of, for example, a radio counterpart. And we can look at the, and also optical off axis afterglows. Okay, so, so let's look at this question. Okay, so I think Brian already showed this. Our expectations for on-axis detections coincident with LIGO sources, if they're all neutron star binaries, it's going to be fairly rare, something like one every couple of years. But what about off-axis emission? So the first thing we can look at is off-axis optical emission. And one thing we can do is we can take the measured on-axis brightnesses, and you can see that they agree with these green and yellow models, which are models with 10 to the 48 to 10 to the 50 ergs of energy and densities between 10 to the minus 3 and 1. Okay, so those, and I told you the typical number is 10 to the 49, and the typical density is 0.1, so right in the middle of this, right? So, so that's our typical afterglow. And now we can ask, what are these going to look like off-axis? Okay, so if we go to an angle that's twice the opening angle away from the center of the jet, these same curves turn into these curves. So the green one turns into that green one, and the yellow one turns into that yellow one. And the reason there is an initial rise is because we need to wait for the jet to the Lorentz factor to decline, the jet to spread out, and come into our line of sight. So by being off axis, we delay the peak, and we also shift the brightness down. So now you can see that if you go to twice the opening angle, then these green and yellow curves become significantly dimmer than when we view these on axis. At 200 megaparsecs, there's somewhere in the range of 23rd to 24th magnitude. Okay, and on here we drew lines of what are the sensitivities of different facilities, PTF, Pan-STARRS, LSST. So you can see that you need something like LSST, an 8-meter wide field telescope, to robustly be able to detect something like that, and that's at only twice the opening angle. If you go anywhere beyond that, it's undetectable. And the fraction within twice the opening angle is maybe as high as 10% of the sources. Okay, so maybe for 10% we might actually catch the optical afterglow as the counterpart to a LIGO source, but not for a larger fraction than that. Now, part of the reason for this is that when you look at something off axis, by the time the jet opens up and comes into your line of sight, the peak of the emission is down in the radio. And the optical, you're looking at kind of the tail of the emission. So that tells you that in principle, the place to look is in the radio. And that was pointed out in a paper by Udi Nakar and by Tzvi. And there are fairly straightforward ways of estimating the brightness and the time scale on which that emission will be detected. And the brightness depends on a combination of the energy, the density, and the velocity of the outflow. So the velocity for something like an off-axis jet will be beta of about 1. Okay, it'll be mildly relativistic when it comes into your line of sight. But this also, the reason they included this is because there's also a component that's mildly relativistic to begin with. The same ejecta that produces the kilonova will also interact with the surrounding medium and it will also produce emission. And it has a velocity that's more like maybe 0.2 c or something like that. Okay. So you can ask the question then, in this energy versus density diagram, if I had to scan 100 square degrees with a radio telescope to find this emission, what part of the diagram is accessible? How much energy and density do I need to make it detectable? And it's essentially everything above these lines for these parameters. So there are two different models here. One is an off-axis GRB, so an energy of 10 to the 49, density of 0.1, beta of 1. And the other one is a more kilonova-like. It has more energy, 10 to the 51 ergs. The density is still 0.1. And the velocity here, we were kind of generous. We used 0.3. Okay, it's probably more like 0.2 or 0.1. So this part is detectable and this part is not detectable. And you can see that all of the short GRB observations are putting us in the non-detectable part. Now that's for scanning 100 square degrees with a radio telescope. There is a different approach, which is if you could identify potential counterparts and only go after a few sources, then you can go much deeper because you don't need to spend all of your time looking at empty sky.
What's the limiting sensitivity that you have that you're using here?
About 0.1 millijansky.
You can do much more.
Yeah, but not at 400 square degrees.
You have-
So that's what I'm saying,
You
that-
have you have a few years to do this, so
Yeah,
you
but
can
it,
do easily much deeper.
no, not easily. So I think if you're looking at individual sources, you can push this line down maybe by a factor of 10, let's say, at best. So that means that some of these will become detectable. But I really think that if you're trying to scan huge areas, then it's extremely difficult.
Is that the take-home message? It's better to focus on a small region but go deeper?
Well, the take-home message is, the point is, as Tzvi just said, the radio emission is anyway delayed. It doesn't happen very quickly. And I didn't put the formula here, but the typical time scale to reach the peak brightness is anywhere in the months to years range. Okay, so you have time. So if you could do a search, let's say, for a kilonova and find a few candidates that you think, okay, those are potentially candidates for the counterpart, then you can go and study those few events in much greater detail because you don't need to spend your time scanning huge areas of sky. You can go deeper with a lot less observing time. It becomes a much easier problem. And there's this natural separation of timescales anyway. So you can do that. So I think that would be the best strategy for this.
How do you get it down to a few candidates? How would you?
So I'm saying if you do an optical search first for a kilonova counterpart, and let's say you end up with a few, because that happens on a timescale of a few days.
Yeah.
Right,
Okay.
and then you build from there. Okay, so that brings me up to this final point, which is the kilonova. So now the kilonova in principle is isotropic, right? So it should be viewable from all directions. But as we already discussed quite a lot, this is not a very bright signature, even at 200 megaparsecs. So we've been looking at, if we take the models from Denkaisen, including the new lanthanide opacities, and we can just ask how bright would that signature be for a typical ejecta mass, let's say 1/100th of a solar mass. Okay, so we can look at this in 3 different filters. So this is the R band, which is relatively blue, I band, which is redder, Z band, which is close to 1 micron. So this is all in the optical. You can see the typical brightness. Okay, so to detect 50% of the sources, for example, in R band, you need to go deeper than what LSST can do. So that's not good. But because these sources are very red, if you go to the much redder filters, you can see that the ability to detect them becomes easier. Maybe you only need to go to magnitude 22 or 22.5. And now you have telescopes like Pan-STARRS and the Dark Energy Camera and LSST that can find this. Okay. Now, if you want to actually catch these sources on the rise, you can measure the rise and the peak brightness and get detailed measurements, it becomes a bit more challenging because you still need to image a very large area, so it takes time. So we've done essentially a Monte Carlo simulation where we asked, in order to not just detect the source, but to capture it on the rise, what kind of observation do you need to do? So for example, in this reddest filter, you need to start within 12 hours and go to magnitude 22. If you want to do it in I-band, you have to start within 6 hours and go to magnitude 23. So I guess the take-home message here is that it's a challenging problem, but it's not impossible given some of these bigger telescopes. But you can see that there aren't that many telescopes that can do it. So that means we have to line up all of these resources so we can use them in real time. Now, this only looks at the question of detecting the source. The other question is, if we search such a large area, what's the contamination? Okay. So we've looked at this in a couple of ways. One is to look at what distinguishes these objects from other ones, and primarily it's the unusual opacity. So if we have observations in two filters, let's say I-band and Z-band, we can look at the color as a function of rise time and compare it to different kinds of sources. And generally, you see that these objects separate out. They're much redder and they have a short time scale compared to most other known or hypothetical transients that people have been talking about. Okay, most other things have longer time scales and are significantly bluer. So there's potentially a way of reducing that contamination. So the final exercise we've done, and we're on the verge of finishing this up, is we actually went out and did the observations. Okay, so instead of just asking this from a theoretical point of view, we imaged 100 square degrees for a whole week in I-band and Z-band to the right depth that's required to detect a kilonova. And we covered these two regions. And essentially, we now have the data that will answer the question of how much contamination is there, because there is not going to be a kilonova in there.
How were they chosen?
More or less randomly, in the sense that we wanted to stay away from the plane of the Milky Way. And we wanted to cover one region that's focused more on environment. So this is a galaxy cluster with a lot of ellipticals. This is more of a kind of field environment with more star-forming galaxies. So we wanted to look at a range of environments and then stay away from the plane of the galaxy. So these observations, I think, will tell us, once we're done with all this analysis, it's an enormous amount of data, what kind of contamination we have to deal with. The nice thing in doing this exercise also is that now we have a data reduction pipeline that can do this in real time when we actually do follow-up, because it's taken us 6 months to analyze the data, which is not something we want to do in the future. Okay, so hopefully at some point soon we'll actually have these results out. All right, so yeah, let me just leave the summary up and take any other questions.
That rate has now narrowed down compared to what I saw last year, I guess.
The rate?
I mean, the prediction rate for LIGO, 5 to 50. You have 200 or something like that. I don't know, is that because of some more data and analysis?
So I'm not sure I recall that, but I'll take your word for it. I think we do have more measurements of opening angles.
Okay.
It's a difficult measurement, so we kind of infer a new one, maybe one per year. So I don't know when the last time was that I showed this, but
This was in Yukawa last year.
okay, so at least a year ago. So maybe we got 1 or 2 cents then to narrow things down.
You
Yeah.
were very busy following up Kilonova.
Yeah. So again, this number depends also on what we take for the observed rate, right? Which again, as Zvi showed yesterday, there's some freedom there that where we don't know what the minimum luminosity is.
All I'm
and so-
asking is, how low should we be prepared?
You're asking if the actual rate is 1 per year.
The lowest is the one we showed with just how many GRBs. I mean,
Yeah.
between the mergers or GRBs.
Yeah, that's right. So if there's 0 beaming correction, Yeah, if there's no, if the beaming correction is 1, then you should get 1 every 2 or 3 years.
Okay.
Yeah, and then it
You
goes,
can live
should
with
go
that,
on from there.
you
Yeah,
know, 1 before retirement, that's what he's looking for.
yeah, your retirement. Yeah, not mine. Yeah.
Nils wants to kill me before I die, that's what I understand.
Yeah.
I'm have to, right? If I'm gonna kill you, I have to kill you
My
before
question is
you
about
die.
offset.
It's not possible.
Yeah.
Right.
Offset investigation, and you assume you show the result with the Nucleosynthesis case. But how about how does result change if you assume the Nucleosynthesis black hole? Because in the case of black Nucleosynthesis, the primary is black hole and the black hole is much heavier than Nucleosynthesis, so kick is not so severe than the Nucleosynthesis.
Yeah.
And now you observe the larger kick, and it is possible to constrain the result.
So we don't
I'll
get a
let-
huge difference in the velocity distribution between the neutron star binaries and the neutron star black hole binaries
Why?
with what we're assuming. You know, you can imagine it being I mean, your arguments are right. It's just that, you know, in the sense that you can imagine them having slightly lower velocities. They probably have slightly higher merger times, and if you looked at our distributions, it didn't make a huge change. And Chris got the same answer as we got back in '99, so we haven't seen huge differences. They're pretty minor. I mean, one thing that we should do is we have delay time distributions, we have velocity distributions, and then we have the distance it traveled. We should look at each of those individually rather than only looking at the results from population synthesis where it's combined.
Mhm.
How shall we expect Kilonova observations to go in the near future? We just have to wait for the nearby promising.
Yeah, I mean, I
sources.
think the way to find them is, I think there are 2 ways, right? One is to follow up short GRBs and to look for this. Then the event where we have that one potential detection is essentially as far out in redshift as you would be able to detect this. Which means, and that was a redshift 0.35, which means you need a relatively nearby short GRB. And again, the rate is somewhere in the range of 1 per year, maybe 1 every couple of years. So those numbers are not going to increase dramatically very quickly. Then the other possibility is following up LIGO sources, right? And I think that all the numbers that I showed in terms of how deep you have to go and all of that assume that you only need to cover 100 square degrees, which I think is doable. If we need to start covering hundreds of square degrees or 1,000 square degrees, then none of these telescopes can go and cover that entire area to the required depth in the required amount of time. So it might not be feasible to actually detect these sources in the early days of
That's right.
LIGO.
I think, by the time we reach advanced LIGO, these are not hundreds of square degrees. The very first numbers were based only on timing formula, but these have been refined
Mhm.
by using more information that
Yeah.
the network of detectors can give us.
Mhm.
So I think tens of square degrees for at least 50% of the sources by 2019, if not 18, 19.
So you're saying we'll have at least 3 detectors which will be able to localize things up to 10 degrees, but 10 square degrees we
Tens
reach
of-
only with LIGO India detectors, right? I mean, with LIGO and Borgo.
With
and
that
even
would be
Cloudrun.
even more like 7 square degrees, I would say.
But
I
that's-
said tens, not 10.
Okay.
Instead of 100, tens of square.
Yeah,
degrees.
look, the better the localization, the easier it's going to be to deal with just collecting the observations. But all I'm saying is that in the early days, if it's hundreds, I think it will be extremely difficult to.
It will be difficult, but it will still be pursued. So my question is, with 100 square degree error region, how many tiles do you need, and for how long do you have to keep looking at a single tile to maybe find a Kilonova counterpart to a GW where we didn't see that?
Yeah, so it really depends on the telescope, right? So let's put aside LSST, which will not get going until 2021 anyway. So if you look at the things like Pan-STARRS or the dark energy camera or Subaru, so you need a couple of things. You need a big aperture, you need wide field of view, and you need detectors that are red sensitive. So those are, I think, the three primary facilities. And to cover that kind of area to the required depth that I was talking about will take a few hours. So we're talking about essentially taking over the telescope for a night, tiling that whole area, and then coming back the next night and doing it again, and maybe the next night and doing it again. So it's a fairly expensive set of observations, right? Especially when you don't exactly know what you're looking for. I mean, we're guided by theoretical expectations, but who knows what things might look like in reality. And then there's a whole slew of much smaller telescopes, wide field telescopes, half meter, 1 meter, that will, I am certain, will go and do these observations. But my expectation from the existing models is that they're not going to see anything. Or they'll see a lot of things, but they're not going to be the thing you're looking for.
And we need a number of them across the globe, and because it's a very longitude dependent constraint situation, right?
Yeah, so at least, Pan-STARRS is in Hawaii, Dark Energy Camera is in Chile, and Subaru is in Hawaii as well. So there's northern and southern coverage. And
So I guess, yeah, so you were saying that using dark energy cameras taking you 6 months to kind of reduce this and develop this pipeline. I mean, this doesn't, so for all these telescopes that aren't already doing transient science, it sounds like there would be a sharp learning curve towards making them ready to do this. You say,
yeah, this is not.
Subaru will do this or something, but
Oh yeah, no.
that's
This is
the one
not a
that's actually
trivial. This is not a trivial
thinking
observation.
this ahead
Yeah,
of time. It doesn't sound like.
yeah. I mean, the data that's generated is hundreds of or of order 100 terabytes or something like that you have to process. You have to eliminate contaminants that are image artifacts. I mean, it's really a challenging problem. The GRB follow-up that we do is much easier than any of this, right? Because we're looking at much brighter sources and very precise positions.
You said you won't see any. Is it because the event rate is low or the flux is too low?
In our mock search that we did, because the rate is very low, right? So we've looked at this with Pan-STARRS. So with Pan-STARRS, we've imaged 70 square degrees for the past 4 years, deep enough to actually detect something else. But if you look, what's the expected rate? It's we don't expect to see any, right? Because so you really need a trigger to tell you where to look.
Is there something else that could give you an infrared transient? I mean, it's very red.
Not that I can think of. I mean, you need it to be red and also relatively fast on a timescale of a few days, right? And what's doing this for these sources is the very unusual nucleosynthesis. And so I don't think there's anything obvious, but we haven't looked. And so I think once we analyze all this data, we'll be much wiser about what we have to deal with. I don't know, AGN flares. I think those should be blue as well. Stellar flares are usually much bluer and much shorter in duration, so I don't think that should be a contaminant. I don't know. Maybe nature is perverse. Yeah.
Let's imagine to observe a short GRB and then to search for a Kilonova observation a few days. According to what Brian showed first day, if we have something that peaks very early, this is going to be very possible to detect just because there is the afterglow. I wanted to ask if this is a common feature, so if this would be an intrinsic limitation, and if yes, where is the border between the first point that we can detect? Because this in principle would be some upper limit, for example, on the electron fraction of the ejecta.
Yeah, so that's a good point. So, so it depends on the brightness of the afterglow, right? And that depends on the energy and the density. I think that the statement that Brian made is, I think, to some extent generically correct, which is that if you look on a timescale of about a day, generally speaking, the afterglow should dominate. But there could be cases where maybe the afterglow is unusually weak because the density is very low or the energy is low, and the nucleosynthesis doesn't care about that, right? So maybe you can reverse that trend, but that's for on-axis, right? If you're looking off-axis, then that contamination, the afterglow goes away, and then you don't have that problem.
Then you don't have the trigger.
Yeah, then LIGO is your trigger.
Yeah.
I mean, yeah, if LIGO is your trigger. Yeah.
So for this particular GRB, this was one of the first that had the spectroscopic confirmed redshift. very early identification of the redshift play any role in getting the Hubble observations? I mean, was there any, I mean, because this particular event had actually quite a bright afterglow.
Yeah.
I'm just wondering, was there any
So
effects that went into deciding to do Hubble? I mean, in a way that would.
not in a serious way, because it was clear right away from the first observations that there's a fairly bright galaxy there. And so, you know, then getting the redshift of that galaxy is trivial. So that whole effort took less than 24 hours. And once you know that, the fastest Hubble can respond realistically is something like 4 to 7 days anyway. Unfortunately, that's how they do things.
But in order to convince the director, you need to say that, okay, I got a redshift or something, right?
Yeah, yeah. And we do that out of general interest in short GRBs, and so we do go and try to get redshifts right away.
Right, but the question is, can you call the director, say, every time you see a short GRB, can I use Hubble to observe it?
You can try. The worst they can do is say no. Yeah. But again, like I said, you need something at redshifts below about 0.3 or 0.35, and those don't happen very often.
Oh, right. Sorry. Okay.
After him.
So the you have one bullet showing magnetar, but you didn't end up mentioning it. So I think maybe the first step is to, because those predict brighter signals for Kilonova, for Afterglow, those kind of things. And for the survey, probably can try to constrain the parameter space of those. That scenario, the parameter space of magnetars, and then reach the point of this more normal Kilonova.
Sure.
With regard to this, you know, you said we might observe 10% of the sources if we increase to twice the opening angle, assuming it's 30 degrees. How far would you go to say, oh, after this there's not much, no point?
Well, we looked at twice and 4 times. By 4 times, it's hopeless. And twice is already very challenging. So I would say twice seems
So that's why.
safe. Yeah, and going beyond that, I think it's very difficult. And I was going to say something about that. I mean, you would see these in the same. The search would be the same as a Kilonova search. The timescales are actually similar, and the brightness is similar. It's just the color will be very different.
But the color will be very
Yeah, color will be very different. Yes.
Different.
Yeah.
Anyone else? No? Okay, let's thank Edo again. We're resuming 3.
Yeah.